Welcome to our help video on 5-8 practice problems with electron affinity, practice questions on electron affinity. We're going to go over the answer key, and this answer key pertains to the second practice set of questions on the assignment. The first one, you went to the Sophia site, you worked through the 3 or so concept pathways to get a better understanding of electron affinity, and then you proceeded with the second set of questions, and here we are now. Questions 1 through 5 dealt with these two diagrams here, diagram A and diagram B. When you looked at it, they did not tell you who these elements were. It always helps to figure out who the elements are as we're trying to reason out information regarding these orbital notations. So who is this one? First, how did I know this one was silicon? I just count the electrons. 2 and 2 is 4, plus 6 is 10, plus 2 is 12, plus 2 is 14. Silicon is the element that has 14 electrons. We see silicon right here. It's the element on the periodic table with 14 protons. If it has 14 protons, it also starts with 14 electrons. Who's this diagram? 1s2, 2s2, 2p3. That would be nitrogen. 2 in the S, 2 in the S is 4, and 3 in the P is 7. Now, of course, we know that we could tell this was nitrogen another way. This is the 2p on the periodic table of elements. If you look on the periodic table of elements, such as this one right here, this is the first level, this is the second level. This is the 2s, this is the 2p. Who's the third element over in the 2p? It's nitrogen. So I really didn't even need to count electrons. I could just look here and say this one's 2p3, that's nitrogen. Nitrogen's the third one over in a p column. How could I do this, tell this is silicon without even checking? The 3p2. It's the second one over in the 3p. Who's the second one over in the 3p? Here's the 3p, there's the 2p. The second one over in the 3p is silicon. So you could do it many different ways, but now I know that we're dealing with silicon and nitrogen. This chart right down here was not given to you. I just copied that from another one to add it so that when we're going over the questions, it will help you see what the answers are. So diagram B is nitrogen, so I put a B in nitrogen's box. Diagram A is silicone. I put an A in silicone's box. When you're doing these questions, you can print your own periodic tables out and write on those. You could be like, oh, this question's on nitrogen, this one's on silicone. Have that out in front of you. First question, which one has a higher electron affinity? In other words, who needs the electron more? Who needs the electron more? Well, nitrogen and silicone. Let's take a look. Does nitrogen even want another electron? Nitrogen is 2p3. If it's 2p3, it means there's one electron in each of the p orbitals. It is half full. The p sublevel is made up of 3 orbitals, 1 electron in each of those 3. It is half full. We've learned that when the p or the d or the f sublevels are half full, there's some stability that offers. Not a lot, but there's some stability that will offer the element. So nitrogen actually, as it says here, diagram B, nitrogen actually has a positive affinity. It's close to 0, but it actually has a small positive affinity. Why? It's half filled. When it has a positive affinity, it means you have to add energy to the atom to get it to accept the electron. Nitrogen doesn't want an electron. Its stability goes down. Picture stability and energy as a teeter-totter. If the stability side of the teeter-totter goes down, or seesaw, the energy side has to go up. Silicone, on the other hand, I look at the silicone diagram. If silicone could get one more electron, it would go from a P2 to a P3. That would half fill it. Is that a great thing? No, it's not a great thing, but having one electron in each of the p orbitals helps it a little bit. So its stability should go up, and it does. If the stability side of the teeter-totter goes up, The energy side goes down. When something goes down, it means we've lowered it. A minus sign. When something goes down, you put a minus sign in front of it. It's decreasing. Second question. Who has the higher ionization energy? Ionization energy is the energy needed to rip an electron off. We learned in the previous section that as we move left to right across the periodic table of elements, the ionization energy tends to go up. That is because as you move left to right across the periodic table of elements, the atomic radius goes down. In other words, as you move left to right, the atoms are getting smaller. If the atoms are getting smaller, their electrons are more close to the nucleus. If the electrons are closer to the nucleus, they're harder to pull off because the nucleus is what's holding them there. Nitrogen is further to the right than silicon. Secondly, silicon is in the row beneath nitrogen. We learned that the ionization energy tends to decrease as you move top to bottom from the periodic table of elements. Why is that? As you go top to bottom, you're adding on a level every time you go top to bottom. The next row has another level. That other level makes the atom bigger. As the atoms get bigger, the electrons in the valence are further from the nucleus. If the electrons are further from the nucleus, they're easier to strip. So not only is silicon a row underneath nitrogen, which means silicon is bigger, it's to the left of nitrogen, which would even make it bigger still. And you could always throw in the shielding effect as well. The shielding effect says that the inner level electrons get in the way of the pole of the nucleus on the outer level. So the more levels you have, the more sublevels you have, the more stuff that's on the inside of the electron or inside of the atom, the more stuff you have on the inside, the more blockage you're going to have of the pole of the nucleus on the outer level. The inner levels shield the pole of the nucleus on the outer levels. So who has the higher ionization energy? Nitrogen is smaller. Nitrogen's further to the right. It's smaller. It's going to be harder to strip the electrons off from nitrogen. In fact, nitrogen, you don't need to look these numbers up to get them. But nitrogen, it takes 1,402 kilojoules per mole to rip electrons off. Silicon is half that, 787. Even more than that. Nitrogen's very hard because there's some stability here. Nitrogen does not want to give up any of those electrons. It's already stable, so it's going to take more energy to rip those electrons off. Which diagram has a larger radius? Well, we kind of covered that. As we move to the right, they get smaller. Nitrogen's to the right of silicon. Why, as we move to the right, do they get smaller? Because when you move to the right on a given period or row, what you're adding is protons to the nucleus. As you add protons to the nucleus, that means you have more protons pulling on the electrons, which will pull them in more tightly. That's why left to right they get smaller, the increased nuclear charge. And silicon has a whole additional row or level to it. Nitrogen has electrons on 2 levels. Silicon has electrons on 3 levels. So who has the larger radius? Silicon does. Its radius happens to be 118. You don't need to look it up. But it has 118. Nitrogen is only 75. Which diagram above would improve the stability? Well, nitrogen already has a little bit of stability. It has 1 in each of the p's. A half-full p is better than not. If we give an electron to silicon, we give it half full. We would make it half full. That offers a little bit of stability. The real stability comes when the S is full and the P is full. But it is a little bit better having 1 in each. The best thing is to have the S full, which takes 2, and the P full, which takes 6. 2 and 6 is 8. That's the octet rule. Having the S and P full is what the ultimate game is. But by giving 1 to silicon, we would half fill it. A half-filled P is better than a not half-filled P. Silicon would be made a little more stable. we would ruin nitrogen stability by giving it an electron because it is already half full. Which diagram above would the addition of electron be endothermic? Remember, endothermic means energy goes in, endothermic. If for energy to go in, that means we have to add it to the atom. So it would be a positive one. So really they're asking which one would have a positive electron affinity. In other words, the energy goes up. The energy side of the teeter-totter goes up when the stability side goes down. So we would have to add energy, diagram B, to nitrogen to get it to take the electron because it's already half filled, which is a little stable. We would have to have energy to it to get it to ruin that stability. Diagram B would be endothermic. Endo, energy going in, which means it's going up, adding it. Exo means the energy exits or leaves. That would be go down. All right, that's the first 5 questions. We're going to stop the video here. Well, actually, we might have time to go on to number 6 and finish this page off. Let's do it. Which one of these following statements is false? Now, I like to remember, I'm looking for the false statement. So I've highlighted here. Sometimes when you take tests and they're asking questions like that, if you highlight false in one color and true in another color, it will help you remember what you're looking for. So I've highlighted false here in red. On this test, I'll highlight trues in green. So let's take a look at number 6. I'm looking for which of these 5 statements is false. Letter A, atoms with a positive affinity are made more stable. Well, remember the teeter-totter. Positive stability means we're adding. A positive affinity means we're adding energy. Atoms with a positive affinity are made more stable, meaning we had to add energy. Hold on. If we're adding energy, the teeter-totter side of energy is going up. That means the stability side must be going down. So if we're adding energy, we would be making them less stable, not more stable. That's a false statement. That's a false statement. But let's make sure there's no other false statements. Letter B, in general, both the ionization energy and affinity increasing horizontally, left to right. Absolutely. As we go left to right, the ionization energy increases. Why? Because the atoms are getting smaller. As we move left to right, here's the periodic table. As we're moving left to right, the atoms are getting smaller, so the ionization energy goes up. But so does the electron affinity. Why? Look over here. In general, as we're moving left to right, the need for electrons is going up. Fluorine, if it can get one, would fill its outer octet. Oxygen, if it could get one, comes closer to filling it. So over here, if we give them electrons, they really don't come close to filling it. So left to right, electron affinity tends to go up. The need for electrons tends to go up in a very general way. Let's go to letter C. Electron affinity can be expressed as a negative. Yep, we already saw that. Negative means stability went up, energy went down. It can be positive. Absolutely. Positive means stability went down, so energy went up. And it can be 0, which means that often 0 is used to represent anything that's positive. But 0 could also mean that overall there was no energy change. Electron affinity refers to the energy change. It's possible to give an electron to an atom and have it not really want it and have it not really ruin it. That would be a stability or an electron affinity of 0. Electron affinity and ionization energy decrease top to bottom. Well, what happens when we go top to bottom from the periodic table? As we move top to bottom through a group, column, or family, the atoms are getting bigger. If the atoms are getting bigger, their ionization energy decreases. If their ionization energy decreases, that means it's easy to rip electrons off them. If it's easier to rip electrons off them, that means they would have trouble attracting a new electron. So affinity does follow the pattern there. And finally, E, atoms with large radiuses have lower affinities and lower ionization energies. Absolutely true. Absolutely true. The bigger you are, the easier it is to steal electrons. The bigger you are, the worse you are at attracting electrons, which is what affinity measures. Next video, we'll pick up from here.